Welcome to the 50th lecture on the course Advanced Steel Design. In this lecture, we are going to learn more about thin-walled sections. Which will lead to the discussion for lateral torsional buckling. We all know that structural steel is the most preferred construction material for many engineering projects. Structural steel offers more advantages compared to other construction material which is popular, which is reinforced concrete. In fact, there are certain applications where steel is considered to be a non-replaceable only construction material. So, steel has exclusive application dominance. In certain areas like long span roof trusses, pavilions, cable stayed bridges, stadiums, and of course offshore platforms. Steel has got very exclusive advantages. Okay, we have seen them in repeated lectures. Usually, structural steel is available in different shapes. So, we can say they are composite shaped, they have light weight, and of course, thin sections are also used. When we talk about thin cross sections, there is a complexity. In addition to shear, and axial resistance, other parameters should also be checked for design of steel beams and columns when you use thin sections. Okay. So, there are well laid design procedures in design codes. Design checks are carried out with advanced application under the structural response. Therefore, in thin sections, special attention is paid is drawn towards torsion. Let us look at a figure. I will copy this figure here. This is a circular section. Subjected to torsion at one end. Okay. In case of pure torsion, which is referred as Sen-Veron's torsion, so this is a classical example. of pure torsion, which is referred also as Sine-Venance torsion, so let us try to understand this slightly in a better manner. A circular bar of radius r and length L is considered. Okay. This bar is subjected to pure torsion at one of its ends. This is possible only when the other end of the bar is fixed. So, this is a case of one end fixed and other end free, which is similar to a cantilever. Agreed? Now, we are applying a twisting moment of magnitude T at the free end. Okay. This simulates a cantilever beam as well, we have to keep it in mind. Now, under the influence of this torsion, an initial point is shifted to a new position. See this figure? The initial point B is shifted to a new position B prime. Okay. So, under torsion, on the circumference is shifted to a new position B dash. Now, we make certain assumptions. We will say that there is no change in diameter of the bar before and after applying T. So, this imparts a very important condition. This imparts a fact that any section cut normal to the longitudinal axis of the member is circular despite torsion is being applied. That is a very interesting assumption. So, any section cut normal to the longitudinal axis of the member remains circular even though a twisting moment is applied. Okay. So, there is no distortion in the shape of the cross section. because the cross section initially was circular, later on also it remains circular even though it is subject to torsion at one end. Okay. Now, interestingly friends, this condition is valid only if the material is elastic. Okay. Therefore, in such analysis, the material is assumed to be linear elastic. Okay. Also, friends, please note, twisting moment will generate stresses. Okay. They are very small compared to the yield stress of the material. Please understand this. The magnitude of stresses developed because of this twisting moment is very small. Okay. Now, please note, yield stress is a material property under axial stress strain. Please understand that. It is not under any twisting moment. Okay. Yield strength is calculated based upon axial stress strain. But this is a very important assumption we make, so that this is helpful for our analysis. The second assumption what we make is the bar undergoes small deformation. Let us say not deformation, let us call this as a deflection. It is a cantilever bar, it undergoes small deflection. This is a very important assumption because it conforms to the fact that if large deflection is expected at cantilever, then the behavior is of a different phenomenon. Okay. Therefore, friends, pure torsion isolates the effects that arise from deflection of the member, which will be inherently present in the member, but that is being neglected. Okay. In simple terms, when we focus on effect of twisting moment applied at the free end, this end has already undergone a considerable deflection which is oversighted. That is a very important statement we want to make here. The cantilever end is already undergone a significant deflection, but under the application of twisting moment, this deflection is oversighted. We are not looking into it, we are not considering it. Okay. Now, Let us copy this figure. Now, we will equate the external twisting moment to the internal. Okay, we get the following: T internal will be Gj theta by L. We will equate this to external because equation number 1. So, now tau max is G r theta by L, it's a standard expression. Now, let us substitute equation 2 in 1 and simplify. We get T as, let us say, G theta by L is tau max. So, tau max J by R, am I right? Because G theta by L is tau max by R. So, tau max by R into J. We call this equation number 3. Okay. Having said this, we also know that theta will be TL by Gj, which can be written from the simplification. Now, tau max in this expression is the maximum shear stress. At the circumference. Theta is the angle of twist. G is the shear modulus of the material. J by R is termed as torsional section modulus. It is very important to note, friends, except shear stress, no other stresses are developed in the cross section. Okay, in the cross section. Now, when you look at a member under pure torsion, it enjoys one more benefit. Members under pure torsion enjoy one additional benefit. What is that? Cross section rotates as a rigid body. So, what does it mean? No distortion is developed in the cross section. When T is applied, if it is a pure torsion case. Okay. But the angle of twist will change along length of the member. Probably theta will be maximum at the free end where T is applied, and theta will be 0 at the fixed end. Okay. So, theta will be keep on changing along the length of the member. It keeps on decreasing as the section travels towards the fixed end where the twist is 0. So, we should say theta is maximum where T is maximum, theta 0 where T is 0. There is no twisting moment at the end. Okay. But we have assumed that no twist torsion occurs. Okay. So, then what will happen to the cross section? See, you are having a change in theta. So, it has to twist the section, but we said that section cross section shape does not change at all under pure torsion. Then what should have happened to the section? The section undergoes warping. So, in such condition, under pure torsion, the section should warp but pure torsion case confirms also that it does not cause warping. Therefore, the angle of twist is allowed to change, emphasizing the fact along the length of the member is allowed to warp, but warping is same at all cross sections along the member. Okay, that is a beautiful assumption, technically valid. Section is allowed to warp, but warping is same at all sections along the length of the member. Therefore, friends, warping will not cause any additional stresses in the circular cross section. So, twisting produces only pure shear stress, no axial, no bending stress. No axial stress and no bending stress. Okay. Such a behavior under pure tension is perfectly valid for circular cross section in addition to thick walled beam sections. Okay. So, this is also valid for thick walled beam section which is circular in cross section. Okay. Having said this, let us see what happens in case of a closed thin walled section. Let us say a closed thin walled section as shown in the figure. In case of a closed thin walled section, the behavior is different. Torsion of equal magnitude but opposite in nature will be applied to the closed thin walled sections. Let us consider a thin walled section as shown in the figure. Let the length of the section be L. Under the action of applied torsion, one can notice that the point located on the circumference is shifted. Okay. The amount of shift is not same at both ends of the member. For example, at one end the shift is B dash A dash, at the other end the shift is B A. Now, the shift B dash A dash is not same as B. They are different. For a thin walled section, namely tubular or shaft section, one can say the Sen-Venon's torsion constant is given by the following equation. Sen-Venon's torsion constant J is given by J equals phi dO4 dI4 by 32, because equation number 5, and tau is TR by J, which is 6. Friends, even in closed thin walled sections, only pure torsion is developed. Okay? Most importantly, J is not the polar moment of inertia, but it happens to be same as polar moment of inertia. Okay? But it is not so. Okay? Hence, friends, Sen-Venon's theory is perfectly true for circular sections. So, Sen-Venon's theory of pure torsion is true for circular cross sections of thin walled tubes, but not true in case of thin walled I section, channel section, L section, etc. So, only for circular this is true. Then you may ask me a question, in these following sections what happens additional? In thin walled open sections like T section, channel section, angle sections, additional stresses will be developed. It will also experience distortion. Okay. Let us take for example an I section as shown in the figure. So, look at the I section as shown in the figure. So, this is my plan view, okay, of the top flange. This is plan of the bottom flange. And this is simply a view shown here. It is an open thin walled I section. Okay. Let us consider this figure with I section fixed at 1 end. Okay. A clockwise torsion is applied externally. Let us apply a clockwise twisting moment. Externally at one end. The section will twist as you see on the figure. Okay, very important observation. Section will twist about its CG. First observation. Second observation, you will see that the top flange is horizontal at the fixed end, but twisted at free end, correct? Same with the bottom flange also. Is it not? So, now one can say the twist is seen in every section along the length of the beam. This twist is seen in every section along the length of the beam. Okay, the top flange is twisted to the maximum, we can say, top flange is twisted to the maximum at the free end and 0 at the fixed end, which means that twist is imposed on top flange at every cross section along length of the member. Okay? So, twist is imposed on the top flange at every section along the length of the member. Further, this twist is not equal at different sections cut along the length of the member. Is it not? Because how we can say this? It is maximum at the free end and 0 at the fixed end. So, it is not same. Okay? So, when I have a twist in the top flange which is happening at every section along the length of the member which is also not uniform, we can say that top flange is subjected to distortion, is it not? It implies the fact that bottom and top flanges have twisted and bent as well. See the figure? There is a downward deflection, I am marking the point here, from here to here, there is a downward deflection, okay, but from here to here there is an upward deflection. So, what we can say here is, in addition to twisting, both top and bottom flange planes also bent. Is it not? So, therefore, the top and bottom flanges do not remain plane anymore, they are subjected to warping. Okay. Furthermore, one can also notice that the top flange laterally moved to the right side while the bottom flange moved to the left. See the figure here? Top flanges moved to the right while bottom flange moved to the left. Am I right? Is it not? Which means that both top and bottom flanges move in the opposite direction laterally. So, therefore, both flanges move laterally in the opposite direction. These lateral movements will now cause additional moments. Okay, at the ends to counteract. Hence, moments occurring at the top and bottom flanges in the opposite direction will cause warping in the cross section. In addition, these moments will also induce longitudinal stress and strain. So, therefore, friends, in an open thin walled section other than circular, application of torsion resulted in shear stress, which also caused additional bending stress. Hence, the total external torsion can be expressed as the sum of pure torsion and warping. Hence, the external torsion is now the sum of pure torsion and warping. So, T will be equal to Tv plus Tw, because equation number 7. Okay. Now, having said this, please pay attention to this figure where the rotation is indicated as theta or phi, and each displacement laterally of the top and bottom by one delta is summed up as 2 delta. Okay? And there is a moment caused or a couple which is effective with an horizontal force H separated by height of the member. Okay? So, this is a figure which shows twisting in open thin walled sections other than circular. It is a nice section. So, the twisting moment applied at one end can be seen as a sum of pure torsion and additional moment Tw. So, I can now say pure torsion plus additional moment. This additional moment is caused due to the lateral sway of top and bottom flange. So, they move by the same amount delta. So, the net sway is 2 delta, but they are in opposite direction. Now, moment developed due to this is called as flexural twist, which I call as Tw, causing warping. Okay. It also idealizes that each of the flange bends as a rectangular beam about its minor axis. Okay. See here, each of the flange bends about its minor axis a rectangular beam. That is an assumption we make. Okay. So, friends, in this lecture we started learning the behavior of thin walled open sections, thin walled closed sections which are circular, which represents the fact of pure torsion or otherwise called as Sen-Venon's torsion. On the other hand, if you have open thin walled I section, for example, they undergo warping. Okay. So, now our job is to find out the behavior of such sections under warping and try to develop a governing equation for the effect of torsion on such sections. Okay. So, we will discuss this in the next lecture. Thank you very much and have a good day. Bye.